All right, good morning. So here we are again for yet another level lesson of MENG 3310 fluid mechanics. So this is the second lecture in this lecture series, the second lecture of this class for the semester, and we have a few objectives for today's lecture. First, I wish to define and apply the ideal gas law. Second, define viscosity, both absolute and kinematic. 3, describe behavior of Newtonian fluids. And 4, examine the bulk modulus or compressibility of fluids. So, first of all, let's review what it means for, let's review a bit of the ideal gas law. Okay, and I'm going to make sure we're recording. And we are, so we're good. All right, so ideal gas law and perfect ideal gas law, essentially. So ideal gas law, let's review a bit of the ideal gas law. Ideal gas law. So if we review, consider a system of 2 pistons with 2 different fluids within it. Let's say I have one piston here. And the piston, again, if you're not familiar, is just a simple device, a cylindrical device usually. So this would be a cylinder. There is a cap on the top of this with a plunger that can go up and down, and the sides are sealed so they will not leak. And so let's say I have 2 pistons. And let's compare how both liquids and gases, both fluids, behave under pressure or under force as well. So let's say I have in one of these, I have water, and in this one I have air. Now in both of these I apply a downward force P, and let's see what happens. Well, obviously in this one, since we recognized that that liquids are largely incompressible, when I put a force down on this one, the volume does not change. Largely does not change. Now, if you really want to be pedantic, you can say that yes, under pressure, a liquid like water will slightly change, but you're talking 0.001%, something like that. Really a rounding error, a very small change in volume. But something like air or any other gas, the volume of the air will change. Volume does change. So if I were to summarize this, the adjective we had to describe this, of course, is this is incompressible. Generally, as a general rule, liquids are incompressible, while gases are compressible. And that is one easy way to distinguish between the liquid and gaseous phases of matter. So yes, again, when this thing, when a force is applied, the piston will end up going down more towards here, and all of the air will end up down in this little pocket down here. So based on the pressure P applied to a volume, the volume will change, and the density of the gas thus changes. So when you have a sealed container and you apply force to that container, or apply pressure to that container, the density of the gas will actually increase. And there is a simple expression for the density of a gas, and it's related to both temperature and pressure, and this is simply rho gas is equal to P over RT. And this is a particular expression of the ideal gas law, which you learned in chemistry class all those years ago, perhaps. In chemistry class, often you see it referred to as PV equals nRT, but using some simple algebra and some definitions of things like density, mass, molar mass, things like that, you can actually derive something of this form. And then, so P is the absolute pressure. That is key. And we will, after this, talk about what the difference is between absolute and relative pressure. Absolute pressure, so we're talking about ABS, absolute pressure. And this would be in pounds per square foot or newtons per meter squared. So something like PSI, PSF, pascals, or newtons per meter squared are all units of pressure, and although in this case we're talking about absolute pressure. R is going to be your gas constant, and you'll have different values of the gas constant, which you can find in your textbook, and they really vary just depending on what unit system you're using. The one I always remember is 0.08206 liters atmospheres over moles Kelvin. Well, that's the chemistry one. That's probably not the right one you want to use for fluid mechanics. And T, of course, is the absolute temperature, if I can figure out how to write properly. T is the absolute temperature. And this is going to be, of course, in degrees Rankine or Kelvin. Degrees Rankine or Kelvin. Can y'all read that orange in the back? Can y'all read that orange in the back? Okay. Okay. I'll try to refrain from using it then. This is in, this says PSI, PSF, pascals, newtons per meter squared, and degrees Rankine and Kelvin. All right. Questions on that? Fairly straightforward? Okay. And as a review, I'll be posting the slides on the website if you don't catch something. Okay, so let's talk about what exactly I mean by absolute pressure. So we've covered, again, in the previous lesson, we've covered, we've covered the specific gravity, we've covered density, specific weight, and now we need to just talk about pressure, because pressure is a quantity or a variable or a property that is absolutely critical for a course like fluid mechanics. So let's talk about pressure, and in particular, let's distinguish between absolute pressure and gauge pressure. So absolute pressure, so I want to distinguish between absolute pressure and gauge pressure. Absolute pressure is a pressure in relation to absolute zero or absolute vacuum. In relation to an absolute vacuum. Absolute, if I can't write A's properly. Absolute vacuum. In other words, if I had a vessel and I put that on, if I had an example here. If I had a piston and then I had a gas here and a vacuum here, what kind of force would I need to exert on this cap here in order to prevent the gas from moving it into the vacuum? That is absolute pressure. We're talking about pressure relative to a perfect vacuum. And at first this seems fairly straightforward, but then you realize most of the pressures we deal with in terms of pressure measurement, things like that, usually we're actually working with gauge pressure. If you have, say, like your tire pressure gauge or something like that, that's going to be gauge pressure rather than tire pressure. And when I say perfect vacuum, absolute vacuum, I'm talking the idealized vacuum where there's literally no matter present at all. Even the vacuum of space is not a perfect vacuum. There's a few stray atoms here or there. In the vacuum of space, it's not a place you want to stand in, but it's not a perfect vacuum. Close to the Earth, there's obviously a fair bit of atmosphere there, not enough to cause really friction for high satellites, but there is some there. Further away, like in interplanetary space, the vacuum is better. In interstellar space between stars, it's even more. It's even less dense, and then finally, you can look at intergalactic space, and you're at that point you're talking about, a few atoms per square meter or per cubic meter kind of densities. So just insanely low densities there. But there is no such thing as a pure vacuum. And even in laboratory conditions, we will rate vacuums in terms of how good they are. It's kind of like absolute zero in temperature. You can define something as absolute zero, where say all molecular motion ceases, but you can't ever actually get there. In say in a lab or something, you can get pretty close, but you can never get exactly to absolute zero. It's just one of those impossibilities. Okay, then gauge pressure. It's pressure relative to local atmospheric pressure. Relative to local atmospheric pressure. Well, now I have a problem in that I need to actually define what the heck atmospheric pressure is. So consider a column here. So let's say I have the ground here. And then let's imagine I look at a cylinder of air, 1 centimeter square in area, going all the way up from the ground to the end of the atmosphere. So this is, end of the atmosphere, although as we know, the atmosphere doesn't just have a hard boundary. It doesn't just stop at some level. It just sort of slowly decreases in density as you go higher and higher. But if we define this if we define the end of the atmosphere as some point where, at the height where 99.9% of the atmosphere is below this level or something like that, that would be a reasonable definition for the end of the atmosphere. End of atmosphere. And let's say this has the cylinder. So I'm going to take an imaginary cylinder of air and say this has an area of 1 square centimeter. And this here will be ground again. This is ground at, say, sea level. And imagine I were to build, say, a glass tube all the way up. Let's not worry about how we're going to support this thing. That'd be quite difficult structurally. But let's say somehow I'm able to build a glass tube all the way up. And so it's completely contained on the sides, but the bottom here feels the full pressure from the atmosphere. And so the question is, how much mass is contained in that cylinder, or how much weight? And it turns out it's approximately 10 newtons. So at approximately, so I should say at the bottom of the cylinder on one, that doesn't sound like a lot, 10 newtons, right? That's not very much at all, right? But then when you when you think about that, 10 newtons, that's 1 kilogram, right? That's approximately 1 kilogram, the weight of 1 kilogram approximately. And that's on 1 square centimeter of area. You imagine what that's a very small area. It's like this. And so that's sitting on top of you right now. There is every square inch of your body, or every square centimeter of your body, it's much worse for every square inch. Every square centimeter of your body right now has 1 kilogram of mass piled on top of it from here to the edge of space. And, that's a lot of mass, isn't it? How come you don't feel that? Exactly. You don't feel that because there's also pressure pushing out. Exactly. In particular, most of the stuff your body is made of your body is mostly made of liquids and solids, primarily liquids, and those are largely incompressible. The parts of your body that are gaseous, say the air in your lungs, well, that's at the same pressure as the air outside of your body, and so it's not a problem. The pressure internal is the same as the pressure external. Now, you've probably seen some videos around you can find them on YouTube and such. Just search air sucked out of oil drum or something like that. There's several demonstrations I've seen where someone will go and attach a hose and a pump to, say, a big 55-gallon oil drum, suck the air out of it, and just watch the atmosphere crush this solid steel can like it's a tin can, like it's nothing. And so, again, from all this, though, so when I say this, the reason we focus on gauge pressure is that that's what objects really tend to experience. Gauge pressure is what really puts a force on objects. It's what really puts stresses on objects. So that's what we're really going to focus on mostly in this class. But the relationship between absolute gauge and atmospheric pressure is as shown here. The absolute pressure will be equal to the sum of gauge pressure plus atmospheric pressure. Any questions on that? Okay, hopefully fairly straightforward. All right, so let's look at an example of this. And this is going to be example 1.45 in your text. So let's take a look at this here. So let's say we are given, that we have nitrogen N2. It has a density of 4 kilograms per cubic meter. So all this is given. And a pressure of 400 kilopascals absolute pressure. 400 kilopascals absolute pressure. And if at any time you can't read my terrible handwriting, please raise your hand. I'll be feel free to raise your hand, and I'll try to fix that. And find the temperature in degrees Celsius. So this is going to be a fairly straightforward application of the ideal gas law. So solution. And I try to do all of my example problems in this sort of given find solution format. And so, well, let's see. Let's start with the ideal gas law. Rho equals P over RT, like I said before. And, we are told that P equals 400 times 10 to the third pascals. I've converted from kilopascals to pascals. Or this is also 400 times 10 to the third newtons per square meter. And then R, looking in the book, I find that R, a good R to use, will be 296.8 joules per kilogram Kelvin, sort of the metric one. And that's like kilogram Kelvin both in the denominator, which is also equal to 296.8 Newton meters per kilogram Kelvin, like so. And so then I just go and solve this equation for T. It's fairly straightforward. T is 400 times 10 to the third Newton per meter squared over 296.8 Newton meter per kilogram Kelvin, and then times 4 kilograms per cubic meter. And this then comes to 337 Kelvin. And of course, if you remember from our chemistry class days, we do not put a degree sign on Kelvin just because it's not a degree, it's just Kelvin. Named after good old Lord Kelvin back in the 19th century. So lovely. All right, any questions on that?
For test questions or any other situation, do you want us to be very specific as far as the units we use?
In terms of units that you use on exams and such like that, the question was how specific do you need to be on units for exams and things like that? On some of the longer problems, I'm really not going to mind if you don't list all the units in your work midway, but do make sure you have your units in your final answer. And do show your work and things like that. But especially on some of the longer problems, we'll do problems later in the semester that, take 2 or 3 pages of work to work through. And it can be very onerous, especially in exam periods, to write out every one of those units all the way through, all the way along the line. So, but do make sure you at least always put the unit in the, on your final answer, I do want to see your units, the correct units. Okay, other questions? All right, let's move on, and I want to talk next about viscosity, which will be covered on your first homework assignment. All right, viscosity. What is viscosity? So, when I say the word viscous or viscous fluid, you might be thinking, you might think of something like molasses or syrup or a very thick fluid. And really that's what it comes down to. But there's actually a more precise, more engineering definition of viscosity that we can use. And viscosity is going to be very important to some of our later calculations, especially for things like losses, energy losses in pipes, head loss along lengths of pipe, that sort of thing. It really directly relates to, in terms of how much energy a fluid loses when flowing through a pipe, it really relates strongly to the viscosity of the fluid. So that's why it's important to define this. Now, you've probably heard the term viscosity before, but let's see if we can make a more specific, definition. First of all, a more common definition. This is sort of a what you might find in like a high school textbook, high school chemistry textbook. We could define viscosity as a measure of a fluid's resistance to flow. So this is the kind of thing you were probably taught in high school. This is what you probably saw, something like this in your high school chemistry class. They would just say viscosity, oh, that is the measure of a fluid's resistance to flow. And they'd say, oh, molasses is a very low viscous fluid. Something like a gas is something like molasses is a very high viscosity fluid. Something like a gas is a very low viscosity fluid. Something like that. But we are not in high school chemistry class. We are engineering students. And we need something that is a bit more precise. I want something that I can actually measure. Again, we're trying to get something that we can use for the design of pipelines, for the design of machines. We need something we can actually measure and make predictions. We need something more numeric or more quantitative than just something vague like, oh, viscosity is the measure of resistance to flow. We need something better than that. And so, we do have a better definition, and this is the resistance to deformation and shear. The resistance to deformation and shear. This is critical. See, now we have something we can actually use. I can measure the resistance to deformation and shear. I can measure the force on a fluid that it requires to, I can measure the resistance of a fluid to a shear force. That's something I can actually measure. But something vague like just resistance to flow, I have no idea what that means. But when you start talking about shear, I as an engineer can say, oh, I know what shear is. I can measure that. Now we have something useful. So let's look at a case of fluid between plates, and we can sort of get a feel for what this means. Let's look at fluid between plates. And let's say I have two plates. The bottom plate is going to be fixed, and the upper plate is going to be moving with a certain velocity u. So let's say I have two plates, and these continue on. So I'm going to show this stopping, but it actually sort of continues on. Like it continues on to the left, and it continues on to the right. So we're going to have two plates. Oh, what? That was So again, this one is fixed. This one up top is pulled with a force P. And it moves with a certain velocity u. It moves at a certain velocity u. Now I'm going to let the distance between the plates be b. The total distance between the plates I'll define as the variable b, and then the height up from the bottom plate I am going to define as variable y. Now, So this plate is just moving along at a constant velocity. It's moving along, moving along, moving along. Think of something like a conveyor belt or something like that. Just an infinitely long plate, just zooming along here. And this one is sitting still. And then there's a fluid of some sort inside of here. So again, there's a fluid between the plates. Now, so the question then is, what happens to the fluid? What happens to the velocity of the fluid? Well, fluid doesn't like to make sudden changes in velocity. That is one thing that we learned about fluids. Fluids are sticky, in a sense. They don't like to make sudden changes in velocity. So right at where the fluid meets a plate, right at that, where the atoms of the fluid, right at that tiny little bit of height, where the atoms of the fluid meet the atoms of the plate, they must be traveling the same velocity. So, or nearly so. So down here, the velocity must be 0. Well, up here, they're going to be going at, actually let me label this as just U. So U here and 0 here. And there is a gradient between these. And it's going to be linear. So there's a velocity gradient between these two plates. So again, down here, the fluid is at rest right at the surface of the stationary plate, and up here it's moving right at the velocity of the flowing fluid. Let me just see if I can make this match the. Let me just label this as U. Okay, and so then if I want to measure the slope of this line, well, this would be du over dy. The slope of the line would be the change in u over the change in y for any given y. And then this is, again, I just want to illustrate, we have a velocity gradient. Now, on top of this, I can also look at this in terms of angular shear, or angular shear strain. Shear strain, if you remember from mechanics of materials, is an angular strain. It's an angular shear strain. So gamma, but then the rate of shear strain, as it changes as you go up, rate of shear strain is gamma dot. Again, we've mentioned our boundary conditions that's stuck at the bottom plate and moves with the top plate. So let's see here. Let's work through some equations of, just a few equations here. And we can define what we mean via our strain here. And we can define viscosity. Okay, so first of all, notice du over dy is going to be proportional to gamma dot. Gamma dot is the rate of change in gamma as you go along. And tau is proportional to gamma. Tau is proportional to gamma dot, where tau is our is just our strain here. Tau is our shear. And so again, tau is our shear stress, is going to be proportional to du over dy. And so basically this is something that comes from mechanics of materials, and I'm relating these two this way. Now, what's interesting though is this is proportional. So notice that I'm saying the shear stress is going to be proportional to du over dy, but it's not exactly equal to, it's proportional. And that constant of proportionality is going to be our viscosity. Okay, so tau, basically the relating relationship, the shear stress is going to be mu du over dy. This is one of our governing equations that will be useful for further explorations and for your homework, I believe. Where tau is the shear stress, Mu, this is the Greek letter mu, is our viscosity, or our absolute or dynamic viscosity. And u is the velocity, and y is the height. So again, let me specifically label this. We have two different types of viscosity that I will define. So we'll need to consider both of these. Mu is the absolute viscosity, or dynamic, or simply viscosity. If unstated, we are going to assume that if a problem or a system just says viscosity, we're going to assume dynamic viscosity or absolute viscosity. And the units on this well, the units are FTL. It has dimensions, FTL to the negative 2. So it's going to be pound second per foot squared, or something like Newton second per meter squared. Also, and you can there is also a further derivation in the book you can see for this towards the beginning, page 15 or so. And then a poise is a sort of combination of this, a P, for a capital P for poise. You can also use this, but usually we just use Newton second per meter squared, because this is easy to confuse with pascals or pressure or something. 1P is 0.1 Newton second per meter squared. Now I can also do a tau versus gamma plot and see how that works out. So let's look at a tau versus gamma plot, or gamma dot, or du dy. Basically, as you go higher in the fluid, you will end up with a higher amount of shear stress. If I want to interpret this graphically, I can have something like this. So this would be gamma dot, or du over dy. And this would be tau. And then you would have a curve something like this. There's a linear relationship. The shear stress is going to be proportional to the rate of shear strain, or du over dy. And the slope of this line is going to be our viscosity mu. 1 mu. And this is, again, a linear relationship. True for most, not all, but most fluids. There are some exceptions, but in general, if this relationship is true, by definition, if this is true, this is what defines a Newtonian fluid. You've probably heard that term before. A Newtonian fluid is one where I apply the relationship between the rate of shear strain and applied shear stress is going to be linear. All right, questions on that? I know it's a lot. You probably need to sit down with the bookends before. You'd have to bang your head against the wall before this. I know this is a little. First time you see this is a little bit iffy, but just look at your book, rewatch this. Hopefully that'll clear it up after a bit. I know this is kind of going through a lot fairly quickly. Okay. But there'll be one or two problems in your homework that you have to work through the exact definition of this, but you'll be pleased to know that through most of the course, we don't need to worry too much about the actual theoretical definition of viscosity. Most of the time, we're going to be dealing just with applying the number, essentially. Anyway, so let's talk about temperature dependence of viscosity. So what do you think might happen to how do you think viscosity might depend on temperature? Anyone have an idea? Generally, yes. As it gets hotter, the temperature goes down. So, at least for liquids, huh? Yes, as it gets hotter, the viscosity goes down. Yes, because again, a very viscous fluid. Did I say temperature goes down? Okay, well, it's Friday. Anyway, sorry. As temperature goes up, viscosity goes down. Yes. Now, again, so temperature, and great. There's a recording to prove I did. Great. Yes, I can always edit it later. Yes, it never happened. Temperature dependence. So I'm going to show first the first graph I'm going to show you. We're going to go through a couple different graphs, but the first one I want to show you du versus dy, and then ta for water at two different temperatures. So the first one would be something like here, and that's supposed to be linear. Water at maybe 60 degrees Celsius. And this one is maybe water at 100 degrees Celsius. So Ta can be thought of as the shear force applied. That's one way to think of it. It's the amount of force. It's going to be directly proportional to the force P I apply to the plate to move it. So you notice that for the shallower graph here, for the same force applied, I'm getting a larger deformation. Du dy is basically the deformation. It's how much it's flowing. So for the same, you can conceptualize this as this is force applied and this is how much it flows. So for the same force applied here, if Ta is the force applied, for the same force applied, the 100 Celsius water is going to move a lot farther than the 60 Celsius water. And so yes, as temperature increases, velocity decreases. In fact, you may have even used this. Like one application I've used of this, I know at least in my own kitchen, is sometimes if you buy now if you buy the stuff like just the regular old honey at the store, it's usually has enough stuff in there to keep it liquid. But sometimes if you buy like the fancy honey, like the organic whatever, or something from a farmer's market or something, it actually solidifies in the jar. And the one way to one way to get it to flow again is to, especially if you can do this if it's a glass jar, is just put it in very warm water or even microwave it or something like that. And via raising the temperature of the honey, it actually it decreases the viscosity, and then you can pour it out of the container. Now, so what about gas versus liquid? Now, interestingly enough, you might think that all viscosity goes down as temperature increases, but gases are actually an exception to this. Gas versus liquid. It turns out that the viscosity of a gas actually increases with temperature. So if this is mu and this is temp, you're going to have something like this. So liquid is going to exert something like a kind of behavior like this. It's not linear, the relationship of viscosity versus temperature, but it generally decreases as the temperature increases. But gases will actually exhibit kind of the opposite behavior. Let me do more like something like that. It's actually going to increase with increasing temperature. Basically, the reason for this is that liquids will see a weakening of cohesive forces. This makes them easier to move. However, gases by their nature don't really have much cohesive forces present in them. So, but as you increase the temperature, they're going to be jostling up against each other more and more and more. So that means more collisions, that means more interference to flow. Let's see. Does that kind of make sense? Although there aren't probably many applications where you need to, actually there are a fair number of applications where mechanical engineers will need to consider the viscosity of even something like air. If you're designing, say, an HVAC system for a large building, you are definitely going to need to worry about the viscosity of air. Because, obviously, if you have a large building, sometimes the size of air pump that you're going to need, or the power of an air pump that you will need to force air through all of the air vents in a building, that is directly related to the viscosity of air. It's how resistant it is to flow on itself and against the walls of the ductwork. And that's what's going to determine how big of a pump you need to bring in fresh air to the whole building. Now, let's see. Uh-oh. Oh, no, we're good. Okay. Let me save these just in case. Okay. Don't want to lose that. All right, now let's continue. So, and basically I would like to give maybe some examples of a few values for viscosity. Air generally has a low viscosity, has a very low viscosity. It's easy to move. We know this from experience. In fact, for a lot of history, people didn't even realize air was a thing. There's some famous story. I should look it up and put it in the slides somewhere. But there was some famous story of I think it was in the 18th century or something like that. There was one of those famous early chemists or physicists who he went to the he was one of these people who experimented on early pneumatics and things like that. And he actually went to some rural, far off hinterland village in England. And he was trying to convince the everyday people that, air was a thing, that air actually existed. And so the way he did to prove it was he had two enormous half spheres of cast iron made. And, he showed the people that, yes, you have these two, it was like a hollow half cylinder. And he showed that they're just ordinary cast iron half spheres. Those aren't really ordinary, but just common metal. There's nothing fancy. There's nothing weird going on about this at all. And then what he did was he simply joined them together, not with any glue, not with any adhesive or tar or any kind of nails or bolts or anything. He just put them up against each other on the surface. And then there was a hole in one of them that he could pump the air out of them. And then he asked then he just said, okay, now pull them apart. And so the biggest, strongest men in the village tried to pull it apart, and they couldn't do it. And then the farmers got their teams of oxen and tried to pull on it with all the might of their oxen and everything else. And he demonstrated pretty clearly that yes, there is something here, and we call this the atmosphere, and we call this now atmospheric pressure. But for a lot of history, people didn't even necessarily recognize that air was even really a thing. So anyway, that's neither here nor there. Water is more difficult. Approximately 50 times more than air. If you have something like motor oil, like SAE 30 oil, that's even more viscous. That's about 300 times more than water. Something even thicker like glycerin. Glycerin, if I can spell glycerin, is approximately 5 times more than SAE 30 oil. And then finally something like molasses is approximately 5 times more than glycerin. And finally, I'll define a term, well, not quite finally, just for finishing up my definition of viscosity. I will say I want to mention kinematic viscosity. If you remember back to high school physics, the difference between dynamics and kinematics is that dynamics deals with things like actually having masses and forces and things like that, where kinematics is something like, I throw a ball up in the air and how long does it take to hit the ground? That is kinematics. So I'm not telling you how much the ball weighs, I'm not telling you its mass, I'm not telling you its surface area. I'm just talking about simple objects under accelerations. So that's the definition. That's the difference between kinematic and dynamic quantities. Kinematic viscosity. Now, I am going to use a peculiar Greek letter that we don't see that often, and it looks like a crooked V, but this is the Greek letter nu. So Nu, Greek letter nu, Nu. So again, this is the Greek letter pronounced nu, if you don't know your Greek alphabet yet. And the definition of kinematic viscosity, thankfully this one isn't that tough to remember. All we need to do is say nu is equal to mu over rho. Nu equals mu over rho. Isn't that a beautiful equation? Just entirely a bunch of Greek letters. I love it. It's beautiful. Just so wonderfully incomprehensible to somebody who hasn't had some engineering or science background. Just isn't that beautiful? Just okay. Anyway, and sometimes people do use there is a special unit that sometimes people use, and that is called a stoke. Although we won't really use it that often, but sort of a bit of trivia. A stoke, it's sometimes used in certain industries, is going to be equal to 1 stoke equals 1 centimeter squared per second. All right, questions on any of that so far? We have one more topic that I want to cover, and then I'll let you go. I want to cover a bit on compressibility of fluids and bulk modulus. I want to introduce that topic. Any other questions? Okay. Okay, so compressibility of fluids. We've already mentioned that fluids can be compressed. Bulk modulus is used to sort of describe or characterize compressibility. Used to characterize compressibility. Compressibility. And it basically describes how a change in pressure causes a change in volume. So I'm going to use this equation here. E sub V equals, this is a differential relationship, negative dP over dV over V. So this is the change in volume in unit, basically the change in unit volume under the change in pressure. And so that's one equation we'll want to be aware of. The compressibility of fluids. And units for this are F, L to the negative 2, so same as pressure, because it's just pressure over volume. And so the reason it's negative there is that if you have an increase in pressure, it will cause a decrease in volume. So that means a positive dP will have a negative dV, which means the whole thing will come out as positive. So, and in terms of what this means, let's say you have a fluid that you have a before and after. Before, after. And I'm going to apply a pressure to this fluid. So say it originally, it's like here, and then I apply some pressure to it and it goes down here. Well, initially for pressure, I'm going to have P, and then I'll have P plus dP. And then for volume, initially I'll have V, and then I'll have V minus dV. So dV over V is basically the you can sort of think of it as volumetric strain. Where again, P is pressure, dP is change in pressure, OV is volume, and dV is change in volume. And the relationship here is so this is basically a property of the material. Bulk modulus is a property of the material. And so as EV increases, the fluid becomes more compressible. Fluid is more compressible. Or I should say the more compressible the fluid. And again, this is an intrinsic property of the material. It probably changes with temperature and pressure, perhaps, but it is a material property. And another takeaway is that it takes large dP produces small dV at least for liquids. So generally, at least for liquids, a large change in pressure will produce only a relatively small change in volume. All right, I think that'll do it for today. That's what I really wanted to get through. And so, again, we've reviewed through the definition of viscosity, both absolute or both kinematic and dynamic. We've discussed pressure, both absolute and gauge, and we've introduced the concept of compressibility and the bulk modulus of fluids. We'll meet again on Monday for the next lesson, for lesson 3, and as always, thank you.